In middle school geometry, I learned that the distance between any 2 points in space comes from the Pythagoras theorem. But turns out in space-time, the formula for the distance between 2 points is almost the same, except with a minus sign. Why is there a minus sign? What's going on? The answer that I most commonly got was that, hey, that's because space and time are fundamentally different. Yeah, that didn't explain anything. So I looked into the math, which turns out to be equally unsatisfactory. So I thought I would never understand. I would never get a true intuition behind what's going on over here until now. After combining the insights from these 2 incredible books on relativity, my God, it clicked. It made perfect sense. So in this video, we're going to pretend we don't know anything about space-time or this minus sign or whatever, and start from scratch. And not only will we rediscover all the ideas intuitively and visually like we always do, but by the end of the video, you will find it obvious that the distance formula in space-time must have a minus sign. Otherwise, the concept of time itself wouldn't make sense, and our universe would cease to exist. So if you're ready for this, let's begin. So Einstein, where do we start? Einstein says, Mahesh, a space shuttle is traveling from Earth to Proxima Centauri at, say, about 80% the speed of light. And a light beam passes by. What is the speed of light with respect to the ship? We may already know the answer to this, but if we want to understand things deeply, we have to pretend we don't know anything and try and rediscover things from scratch. So let's use the good old Newtonian mechanics. If I wait for 1 second on my clock, the shuttle travels 0.8 c. Let's make c equals 100 units, so the ship travels 80 units. Meanwhile, light itself travels 100 units. So, after 1 second, light is only 20 units ahead. So the speed of light relative to the ship is just 20 units per second. But Einstein says, Mahesh, this creates a big problem. I'm like, what problem? Remember, in physics, being at rest and moving with a constant velocity are exactly the same things looked from different perspective. That's the cornerstone of Newtonian relativity. No experiment can ever tell you whether you are really at rest or really moving at constant velocity motion because that distinction is meaningless. And I'm like, yeah, I get that. Good. Now think about this. If the people on the ship measure the speed of light to be anything different than c, then the laws of electromagnetism is different from them. We have now an experiment that gives you a different result because you're moving. So they would know that they're truly moving, and that breaks the Newtonian relativity. Now, if you aren't convinced, and you shouldn't be, and if you have more questions, and you should, then our previous video digs deep into it in excruciating detail, okay? So feel free to check that out. But long story short, the speed of light must be the same for all inertial observers. Okay, but then how does it work out over here, Einstein? And Einstein says, well, Mahesh, what if moving things shrink in the direction of motion? Then the ship and everything inside, including their rulers, would be shorter compared to ours. And so they would now measure a distance that is larger than what we'd expect. And similarly, what if moving clocks ticked slower? Then their clocks would be ticking slower compared to ours, which means less than 1 second would have passed for them. So look, Mahesh, light covers a much larger distance in a much smaller time in their perspective. So with the right math, the speed just comes out exactly c for all inertial observers. That's how Einstein got length contraction and time dilation. Incredible, right? But wait, Einstein, are you saying that the ship is physically shrinking and that their clocks are somehow physically slowing down? And Einstein says, no, that's an old, outdated idea. The physicist Hendrik Lorentz had already written down these effects mathematically. That's why these are called Lorentz transformations. But his motivation was quite different. He, like many others at the time, believed that light travels through a medium called ether, and it filled the entire universe. But there was a problem. See, if ether fills the entire universe, then moving through space should produce a backward ether wind. And Earth is moving through space, so we should be able to detect ether wind too. But even the most sensitive instruments couldn't detect it. So Lorentz argued There is ether wind. It's just that the wind alters the properties of materials and physically makes them shorter and slows down our clocks just in the right way to hide ether. So that means Lorenz's motivation for these transformations were purely to save ether theory, not to revolutionize physics or anything. But Einstein says, hey, claiming that something exists but you cannot detect it is not very scientific. If you can't measure it, you can't detect it, then maybe it doesn't exist. In his 1905 paper on relativity, look, he writes, the introduction of a luminiferous ether will prove to be superfluous. I love the words they use. So Einstein did what nobody dared to. He said, let's get rid of ether entirely and deal with the consequences. And what's the consequence? These effects aren't physical distortions at all. Just like how motion and velocity are relative, observer dependent, space and time themselves must be relative. That was the paradigm shift. But what does it really mean for space and time to be relative? Einstein says, look, from our reference frame, this shuttle covers about 4 light years in 5 years. But someone moving relative to us will find that the ship only covered 1.8 light years, for example, in just 3.5 years. And the people inside the ship, they will record something else altogether. And the wild part is, we are all correct. So look, space and time are relative to observers. But Einstein, why? Why does our universe behave this way? And Einstein says, well, let's look at what he actually wrote. Here, he writes, these two postulates suffice for the attainment of a simple and a consistent theory of the electrodynamics of moving bodies, based on Maxwell's theory for stationary bodies. So basically, Einstein says, speed of light is the same for all, and space and time are relative, and that's that. There is no deeper explanation. Or is there? This is where Einstein's old math professor from Zurich, Hermann Minkowski, comes in. He looks at his student's paper and says, maybe there is a deeper explanation behind this. And I'm like, Minkowski, what's the deeper explanation? Minkowski says, let's suspend a toy space shuttle in a square frame with lights casting shadows on the horizontal and the vertical walls. Okay. Mahesh, now what would happen to the shadows if the frame tilts? Well, the shadow lengths will change, obviously. But what if there was a shadow person who thinks their universe is just 2D and these shadows are real objects? What would they conclude? Oh, see where Minkowski is going with this? They wouldn't notice the frame tilting. They would just conclude horizontal and vertical lengths are relative. And Minkowski says exactly, they would talk about dilation and contraction and whatnot. But you and I see the full picture. The world is 3D, and the shuttle's length has not really changed. It's only the frame that tilted, changing the shadow lengths. It's just geometry. So Minkowski asks, what if space and time are just like the horizontal and the vertical walls? What if the lengths and the times we measure are just shadows of a deeper reality, a 4-dimensional spacetime? Then we can explain length contraction, time dilation, and all the effects of relativity geometrically. Oh man, this is so incredible. And this is why Minkowski famously said, and I quote, henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Gosh, these quotes are epic. Okay, now you and I might still be wrapping our heads around what's going on over here, so let's take a step back. I mean, usually when we take a relativity course, we just jump straight into space-time, take it for granted and start solving problems and stuff, right? But look at the journey, how it all unfolded. I mean, it first started with Einstein making a big conceptual leap about rejecting absolute space and time. Then his professor, Minkowski, took a second leap, probably even bigger, rejecting space and time altogether as just shadows of a 4D spacetime geometry. This is why I love to learn and rediscover things all by myself. It's so enriching. And one way to do that for free is by using Brilliant, the sponsor of this video. What I love about Brilliant is that it doesn't just tell you how things work. You actually get to play with the ideas. Every lesson is interactive and project-based. You're not solving dry problems. You get to experiment and reason your way through. With thousands of hands-on interactive lessons in math, science, programming, data analysis, and even AI. But what's awesome is that, just like in this video, you can start from basics and then level up to harder challenges until you master the topic. Research shows this is how you become a better thinker. For example, check out their brand new course in programming. You directly start creating an image filter. You first gain some intuition behind manipulating pixels and then get to convert that logic into code. I mean, how cool is that? But what's cooler is that you can get started for free. Head to brilliant.org/FloatHeadPhysics to get complete access for free. You'll also get a 20% off on their annual premium subscription. The link is in the description, or you can just scan the QR code. All right, happy learning. Back to the video. So how do you think Einstein reacted to his professor's idea of spacetime geometry? Well, apparently he made remarks like, "Since the mathematicians have invaded the theory of relativity, I do not understand it myself anymore. These mathematicians with their four-dimensional space are getting on my nerves." Yeah, Einstein and probably a lot of others were not really a fan. They thought this was absolutely unnecessary. So Minkowski, your idea of spacetime is radical, but at this point, it's just an analogy. What convinces you that it is the ultimate reality? And Minkowski says, Mahesh, answer this. Do you think that these shadow people could somehow figure out that they are just seeing shadows, 2D shadows of the actual 3D object? And I'm like, no, because they're confined to their 2D universe, right? No. What if, Minkowski says, what if they looked carefully? They'd notice something strange. Whenever the horizontal shadow shrinks, the vertical one stretches. And maybe a clever shadow mathematician comes along and discovers that if you square their lengths and add them up, that total always stays the same, regardless of how the frame tilts. It would be an invariant. That would make them go, oh my god, this can't be just a coincidence. Maybe we are just looking at 2D projection of an underlying 3D world. So Minkowski asks, Mahesh, what if space and time could be combined in a similar way to get an invariant, something that everyone agrees on? Then we too would be like, oh my god, that can't be a mere coincidence. Maybe we are just looking at 3D projections, shadows of an underlying 4D world, space-time. Okay, this is interesting. We are getting somewhere, but how do we discover this invariant of the supposed 4D space-time? Well, let's get back to the analogy. This time, what if we just hung two Lego bricks? If they are far apart, just like before, tilting the frame changes the shadow distances. But if they're at the same spot, then the shadow distance is always 0. Tilting doesn't change it anymore. So look, if both the horizontal and vertical shadow distance is 0 in one frame, then they are always 0. So Mahesh, what do you think is equivalent of this for spacetime? And I'm like, well, this means if we have events that are at the same place and the same time, then everyone would agree on it? Exactly, says Minkowski. If two bombs explode at different places, one after the other, those events are separated both in space and time. But when you change frames, our theory is that the space-time axis tilt. That's why those separations stretch or shrink. So our friend in another frame may see the explosion happen much closer in space and time. In fact, she might even conclude the time separation is 0. For her, the explosion is simultaneous. But if both bombs go off at the same place and same time, in that case, the separation in space and time is 0. Tilt the frame however you want, 0 stays 0. So everyone agrees on that. Events that happen at the same place and time are absolute. Awesome. So we now have something that everyone agrees on. Whenever we have events that happen at the same place and time, that's an invariant. Everybody agrees on it. But how does that help us in our original scenario? Suppose the space shuttle has a clock on board. When it leaves Earth, you see the clock reads 0. Now, those two events, departure and the clock reading 0, is happening at the same place and time. That means everyone agrees on that. And when the shuttle reaches Proxima Centauri, if the onboard clock reads, say, 3 years, again, everyone agrees on that. So look, Mahesh, even though we all disagree on the amount of distance and time that we have measured with our own rulers and clocks, we all agree the people in the spaceship aged by 3 years. In other words, the time elapsed on the ship, that is the invariant. Now, because everyone agrees on it, we call it the proper time. The symbol we use is the Greek tau. Think of it as the time measured by a clock that's present at both events. That's important. Like, for example, the ship's clock. In contrast, our clocks are not present at both events. We instead rely on our coordinates. So these are coordinate times and coordinate distances. They depend on reference frames. They are the shadows. But the proper time, in some sense, is real. It's like the actual distance between the two hanging Legos. It represents the true distance in space-time. But wait a second. Here, we just looked at the clock that was on board, and that's how we could figure out what the proper time was between the two events. But in general, events don't come with a clock, next to it. So in general, how do we connect our coordinate measurements that we can do, coordinate space, coordinate time, and proper time? How do we do this? How do we do this intuitively, Minkowski? And Minkowski says, well, Mahesh, now to find this connection, we have to use Lorentz transformations and do a bit of math. There isn't a way to do this intuitively. Or is there? Lewis Epstein, who wrote the book Relativity Visualized, one of my favorite books, thinks otherwise. He makes the last conceptual leap. Are you ready for this? Epstein says, Mahesh, everything in relativity can be visualized intuitively using just one fact. What is that? Everything in this universe, including you and me, are traveling through space-time at the speed of light. The reason we can't go faster than light is because we can't go slower than light. The only speed everything can ever move at is the speed of light. And I'm like, okay, that sounds absolutely ridiculous. What do you mean, Epstein? All right, Mahesh, right now, this shuttle isn't moving through space, but it is moving through time. So it's moving in space-time. And in space-time, the speed will always be c, the speed of light. We'll choose c to be 1, okay? Which means right now, that velocity vector is pointed completely in time direction. Wait, so you're saying that right now that the shuttle is traveling through time at the speed of light? What does that even mean? That means, Epstein says, for every second in my clock, the clock on the ship goes ahead by 1 second. Epstein defines the speed through time as the time elapsed on its clock, meaning its proper time, per unit time on our clock, the coordinate time. And here, that's 1 divided by 1. So it's just 1. So the speed through time is 1, speed of light. It basically means its clock is ticking at full speed, the same rate as our clock. Also notice, it's projecting a full-length shadow. So we see the ship to be its full length in space. But what does this whole thing look like from the perspective of our moving friend? Well, since our friend is moving, his frame is tilted so that he sees the ship moving to the right. So look, Mahesh, in his frame, that vector is tilted, but its total magnitude still stays the same, 1. And that tilt explains everything. When 1 second passes on his clock, look, less than 1 second passes on the ship's clock. The ship's speed through time is reduced because part of its velocity is now spent moving through space. That is time dilation. But notice, nothing physically has changed. All that changed is the coordinates. The frame tilted. But wait, there's more. Look at the projection on the space now. It's shorter. That's why our friend measures the ship itself to be shorter. Length contraction. Incredible, right? And the faster it moves, the more extreme these effects get. Finally, when the vector tilts almost horizontal, almost all its velocity is through space. The ship is practically frozen in time. Its length and time intervals are infinitely distorted. This is why light travels at sea through space, because its velocity is completely pointed in space. Thinking of our universe as a four-dimensional space-time is starting to make so much sense. Oh my god. Take about Epstein and of course Minkowski. Quick note though, Epstein's diagrams are not standard space-time diagrams, okay? Look, we are drawing coordinate space versus proper time. Usually when we say space-time diagram and 45-degree light cones and all of that stuff, we draw coordinate space versus coordinate time. But who cares whether it's standard or not? The ultimate question is, can we put it all together mathematically? Can we find a connection between coordinate space, coordinate time, and the proper time? Epstein, how do we do this? Mahesh, let's decompose this velocity vector into horizontal and vertical. The hypotenuse over here represents its total velocity through space-time. This is the velocity through time, and this is the velocity through space. So how do we connect this? And I'm like, well, Pythagoras. Velocity through space-time squared should equal velocity through space squared plus velocity through time squared. So let's simplify. We know velocity through space-time is always 1. What is velocity through space? And I'm like, that's just dx over dt. How much it moves through space per unit coordinate time. Now, what is velocity through time? This is the important one, but it's very similar. It's how much it moves through its own time, proper time, per unit coordinate time. So d tau by dt. Plugging in and simplifying, what do we get? What do we get? Oh, here it is. Here it is. The proper time squared equals the coordinate time squared minus the coordinate space squared. We have rediscovered the ultimate equation connecting all three. This is the distance formula in space-time. Okay, I'm sure we have a ton of questions now, but my first step whenever I rediscover or look at a new equation is to do a sense check, and I do that by plugging in some numbers. So, going back to our space shuttle. Remember, from our perspective, we saw that it covers a distance of about 4 light years in 5 years. Now, those are our coordinate measurements, Minkowski shadows. But if we plug in, we now find the proper time to be 3 years that we saw, right? Okay, meaning the people on the ship are only 3 years old, which means for them, the journey only took 3 years. Exactly like what we saw. But let's check our friend's perspective. She measured the ship covering just 1.8 light years in only 3.5 years. Different shadows, right? Because her frame is tilted. But now she plugs into the same rule and look, she too agrees that the folks on the ship have aged by 3 years. So we will disagree on our own measurements of distance and time because those are just coordinate shadow lengths, which depend on our frames, which are tilted. But the proper time, 3 years, is something that we all agree on. It is the true interval between these two events. It's the invariant quantity. It's the actual distance, in some sense, between the two events in space-time. So, can we now answer the question, where does the minus sign come from? The Epstein's diagram actually helps us see it. From the ship's frame, it's not moving. So its velocity in spacetime is directed upwards, only through time. So at time t equals 0, Earth leaves it, and 3 years later, Proxima Centauri arrives. So it takes them 3 years. But if we look from our perspective, the frame is tilted. But the speed in spacetime is always 1. So look, 3 years are not enough. We need to wait more, about a total of 5 years. And from our friend's perspective, that tilt is slightly less. So for her, the ship only takes about 3.5 years. Which means, look Mahesh, when we change frames, it's the vertical distance that stays the same. That's the invariant. The hypotenuse and the base are the shadows. But in normal space, when we tilt the frame, the hypotenuse is the invariant. That's why in normal space, the formula for the invariant ends up with a plus sign. But it ends with a minus sign in space-time. And since these invariant quantities are real distances, in normal space, the distance formula has a plus sign, and in space-time, the distance formula ends up with a minus sign. That's where it comes from. Here, the distance is just the proper time. But why does it work out this way? What is the core reason? In normal space, you can move at any speeds you want. There is no speed restriction. But in space-time, you can only ever move with one speed, the speed of light, c. As a result, the faster you move through space, the slower you move through proper time. That's what the minus sign is saying. So putting it all together, when people usually say that, hey, the minus sign is because space and time are fundamentally different, no, that's not accurate. What they really mean is that space-time is fundamentally different from space. How different? 2 reasons. In space, it's the hypotenuse that ends up becoming the invariant. But in space-time, it's the vertical leg that ends up becoming the invariant. And in space, you can move at any speeds you want. You have no restrictions over there. But in space-time, you can only ever move with just one specific speed, the speed of light. These two together, as we saw, make sure that we end up with a minus sign in our distance formula. But I promised you full intuition. So here's the last question. What if, hypothetically, our universe had a plus sign in the space-time interval formula? What would the universe look like? Well, remember, in our universe, the minus sign comes from the fact that the total speed through space-time is always 1, the speed of light. So the speed through space or time can never exceed 1. Meaning nothing can ever move faster than the speed of light in space, and no clocks can ever tick faster than, well, what my clock is ticking right now. But if there was a plus sign, then after rearranging, look, we see that that restriction goes away. For example, the speed through space can be 2, and that would make the speed through time 3, meaning we could see things traveling at twice the speed of light, and they would be aging thrice as quickly as we do. The speed through space and time could be as big as possible. There would be no more restrictions. Isn't that awesome? No, because if signals could travel at infinite speeds, then any changes, physical, chemical, biological, could all happen instantly. In other words, the entire history of the universe from the beginning to the end would happen instantly. The universe wouldn't make sense anymore. So look, it's the negative sign that preserves the speed limit. It ensures signals cannot travel at infinite speeds. It ensures that changes don't happen instantly but evolve over time. And this allows our universe to meaningfully evolve. The minus sign gives the universe a meaning. Wow. So, although Einstein initially dismissed Minkowski's ideas, eventually he came around. In fact, when he struggled for years to reconcile gravity with relativity, he realized the missing piece had been in front of him all along. He later writes, I realized that only through Minkowski's four-dimensional formalism does the theory become sufficiently general and clear. So Einstein not only embraced his idea, he took it to an entirely new level, creating general relativity, the most successful model of the universe we have even today. So although Minkowski unfortunately never lived to see it, the very idea that Einstein had dismissed as unnecessary became the foundation for his greatest achievement. I'll see you soon.